Numerical or quantitative data. Variables can be either discrete or continuous. A discrete numerical variable takes values at specific intervals but not in between. For instance, number of siblings, ACT scores, etc. You can't have 1.5 siblings or 1 3/8 of a sibling. You can't get a 27.35 on the ACT. So these are discrete numerical variables. A continuous numerical variable can have any value within a range. So you can be 72 inches tall, or 72.5 inches tall, or 72.25 inches tall, or 72.1 inches tall. It can be anything in that range. Or distance, or time. You can have half a second, or 1/10 of a second, or 100th of a second. You're limited only by the precision of your measuring instrument. So, if you're trying to determine whether a variable is discrete or continuous, think, can I have half or 1/3 or 1/10 of this thing? If yes, it's probably continuous. If no, it's discrete. Not all discrete numerical variables are integers. You may be able to have half of something, but not 1/4 of something. Money, the amount of money, is a discrete numerical variable. You can have 1/100th of a dollar, but you can't have 1,000th of a dollar. So still discrete, even though you can have decimals, because you can only have some decimals. You can't have any decimal. Scatter plots are useful for visualizing the relationship between two numerical variables. Looking at this scatter plot, this is from a really cool website, gapminder.org, which has a whole bunch of graphs where you can plot a whole bunch of different variables. So this is the fertility, the number of children per woman in the population, and the life expectancy in years for 2011 for a whole bunch of different countries. So do life expectancy and total fertility appear to be associated or independent? They appear to be associated. There appears to be a linear trend here. Right? Linearly and negatively associated. On average, as fertility increases, life expectancy decreases. I think I had to go to the website to show the relationship, which I'm not going to do right now. But if you go to this website and look at this graph, you can have it show it over different years, and all of these dots move around, and it's really cool. A scatter plot shows the association between two numerical variables. These following show distribution of a single numerical variable. A dot plot, a stem leaf plot, and a histogram. So, dot plots use dots to show the frequency or number of occurrences of the values in a data set. The higher the stack of dots, the greater the number of occurrences there are for that data point. So this is the number of characters in a whole bunch of emails in thousands. So you've got most of these emails that appear to be less than 10,000 characters, and you've got someone wrote like an entire novel in their email that is over 60,000 characters. 60,000 characters isn't actually a novel, but it's a very, very, very long email. In a stem and leaf plot, each number is broken into two parts. First part is called the stem and consists of the beginning digits. Second part is the leaf and consists of the final digit. Stems are written in ascending order next to the leaf to which they correspond. Always remember to include a legend so that we know if this is 1.2 or 12 or 12,000. Right here, this is the number of characters in the email. That corresponds to thousands. To increase the number of stems, you can also make a split stem and leaf. So here we have a lot of numbers that have zeros as their first digit. So we put 0 to 4 in the first instance and 5 to 9 in the second instance, just so we don't have this line running off the page. Both dot plots and stem and leaf graphs are better for relatively small data sets. If we have this data set 4, 5, 3, 4, 6, 7, 3, 3, 4, 6, 7, 7, 2, and 9, we would rather have a dot plot because these would all be single digit numbers. If we did a stem and leaf plot, it would just be 0, and we've got what? 3, 3, 3, 4, 4, there's a 2 there, 4, 4, 4, 5, 6, 6, 7, 7, 7, 9. Like, that's just a list of numbers. That's not a way, that doesn't display the data in a useful way. Histograms provide a view of data density. Higher bars represent where the data are relatively more common. Your variable goes on the x-axis, and then the frequency, how many, or the relative frequency, which is what percentage, go on the vertical axis. So here they asked a bunch of people how many hours per week they spent on extracurricular activities. 150 people said 0 to 10. Looks like about 30 people said 10 to 20, and maybe 10 people said 20 to 30, and then it decreases from there. This one person has a lot of free time, and I'm jealous. Histograms are especially convenient for describing the shape of the data distribution. Note that the bin width can alter the story the histogram is telling. So here, the bin width is how wide the bars are. So here, the bin width is 10, 0 to 10, 10 to 20, 20 to 30. And so from here, we can see that most people are between 0 and 10, and then we've got this like one outlier down here. Right? So here are multiple histograms that are showing the same data with different bin sizes. So which of these are useful? Which reveal too much? Which hide too much? This one does not show you anything. It tells you that almost 200 people have between 0 and 50 hours of extracurriculars, and one person has over 50. That's not helpful. The 0 to 10 is pretty good. This one in 5-hour increments also works. Gives us the general shape. The right skew shows the one outlier. Those work pretty good. This last one is a little bit too fine. That looks like broken down in intervals of 2 hours. And that gives us all of these little bumps where we don't really need them. It just doesn't give us the general shape as well as the others do. Nothing really wrong with it, but it does make this look like there's a second mode there, which is kind of weird. Bar plots are used for displaying distributions of categorical variables, while histograms are used for numerical variables. The x-axis in a histogram is a number line, so the order of the bars cannot be changed. In a bar plot, the categories can be listed in any order, although some orderings make more sense than others. if your categories are grade levels, 5th, 6th, 7th, 8th, 9th, 10th, right? There's an implied order there, even though that's a categorical variable. So you would not want to just put those in any random order. Time for Miss Schumann's favorite game, What's Wrong with This Graph? Top 5 counties with the greatest numbers of confirmed COVID-19 cases over the past 15 days and the number of cases over time. All right, so here we've got 5 counties, Cobb, DeKalb, Fulton, Gwinnett, and Hull. And it looks like COVID cases are declining over time. Yay! It's kind of hard to see in this picture, but if you zoom in, 28th of April, 27th of April, 20-something of April, 21st of May, 30th of April, 6th of May, 4th of May, 5th of May, 25th of April. The dates are not in order. And yes, that was deliberate. They deliberately ordered these from greatest to least to make it look like COVID cases were declining over time. The shape of a distribution is also has to do with the modality. So the mode is going to be the peak, the high point of a graph. If it's got one peak, it's unimodal. If it's got 2 peaks, it's bimodal. Multiple would be multimodal. And no apparent peaks, looks pretty flat, would be uniform. So this is unimodal. Got 1 peak here. This one would be bimodal. Yes, one of the modes is higher than the other, but there's still 2 clear peaks, so that makes it bimodal. This one looks like it's got 3, so this would be multimodal. And this one is pretty flat. This would be uniform. So in order to determine modality, step back and imagine a smooth curve over the histogram. Imagine the bars are wooden blocks and you drop a limp spaghetti over them. Kind of like the drawings that I did on top of these. Distribution, the shape of distribution is also in the skew. So histograms are skewed to the side of the tail. So here the tail goes to the right. This is right skew. Here the tail goes to the left. This is left skew. And this one appears to be roughly symmetric. AP test tip, don't ever say that a distribution is symmetric. You should say approximately symmetric or roughly symmetric. The AP test loves their hedge words. So this is approximately symmetric. We also want to look for outliers. There is, in fact, a definition of an outlier. What is far enough away to be considered an outlier? And we'll talk about that next week. Might be in here. But just to review, shapes of distributions, unimodal, bimodal, multimodal, or uniform. And it can be right skewed, left skewed, or symmetric. Which of these variables do you expect to be uniformly distributed? So uniformly distributed, meaning that every value in the range are going to be approximately the same. Should be D, right? Days of the month for birthdays, you're going to have about the same number of people born on the 1st as the 5th, as the 12th, as the whatever. Weight of adult females are probably going to be pretty symmetric. You've got the majority of people in the middle, and then you've got some very, very skinny people and some very fat people. Salaries of a random sample of people in North Carolina are going to be right skewed. Majority of people are here. You've got a few people, very rich people. House prices, similarly, right skewed. A few very, very, very expensive houses. Sketch the shapes of the expected distributions of the following variables. Number of piercings, SAT scores, income in the US. So for number of piercings, I expect, so let's make this 0, 1, 2, 3, 4, 5 plus. I expect what we would see is that we'd have a large number of people with 0 and a large number of people with 2, right? Both ears pierced. And then smaller numbers of people with more than 2. So I expect this distribution would be bimodal and skewed to the right because you have a few people who have very many piercings. I have a friend who has like 13 piercings now. But you're much more likely for people to have either 0 piercings or 2 piercings than to have 1. Because a lot of people have both ears pierced. SAT scores are going to be roughly symmetric. That is by design. Most standardized tests are roughly symmetric because the tests are designed to be a bell curve. Income in the United States is going to be right skewed. You got most of the people making making under $100,000 a year, and then you've got a few very, very rich millionaires. Cumulative histograms show the proportion up to a certain number. So, comparing these two histograms, right? This bar corresponds to this part. This bar is these 2. This third bar is these 3 together. This fourth bar is these 4 all together. The fifth bar is these 5, right? So the bar here right before 0 is all of these preceding bars added up. Notice that the scales are different. This one goes to 2,000, this one goes to 10,000. So all of these, this bar here that's less than 0, that's at about 5,000, is all of this part. And then your last bar should be your total, because everything is less than or equal to the highest number. Distribution here, right? So what percentage of the people, so you've got an income here at 63,000, and that's 50 because that's the median. 50% of people earn 63,000 or less. Because this is right skewed, your average is higher than that. So 90,000 is your average, and that's like 65% of people that earn 90,000 or less. And then up here, we've got 1 million, and basically everyone earns less than $1 million. So, distribution of total income for U.S. households, for U.S. families, which is a slightly different definition, but you can see the distribution is still about the same. And this is for individuals. The thing about cumulative distributions is that they can't tell us the shape of the distribution. Generally speaking, cumulative distributions are always going to be this kind of S-curve. It could be, if the distribution is uniform, you could have like a straight line, and the more S-shaped it is, the more symmetric it is, I guess, because you're having a big jump in the middle, but it's really hard to tell. This would be, so like a straight line would be totally uniform, and then something with a big peak in the middle is going to be more S-shaped. But you really can't determine shape of a distribution from a cumulative distribution graph. It just doesn't work.